So if you take a molecule called N-pentane, you can write all the carbons in a straight chain, because N-pentane means it's a straight chain compound. Write the molecule in a straight chain and balance the hydrogen by projecting the hydrogen outside, because the valency of carbon is 4. Similarly, if you write them in the condensed form like CH3, CH2, or you can write CH3, CH2 3 times CH3, we call it as the condensed form. Or you write it in a single line like this, it's called as bond line form. Okay sir, other than this, what are the other forms? How do you write the other forms? See, other forms are, you write the same N-pentane in another form called wedge projection. This wedge projection is for a special type of carbon called sp3 carbon, or for tetrahedral carbon. This is not given for all the molecules, only the molecules with sp3 carbon, that is single bond. So let us take N-pentane. So first you should write like this. Check if there are 5 carbons. Among the 5 carbon, like this, 2 lines to be drawn. So in the 4 valency of the carbon, 2 lines will be a normal line. The other 2 lines will be like this, a solid wedge and a dashed wedge. A solid wedge and a dashed wedge. A solid wedge and a dashed wedge. So the remaining part you have to balance it with hydrogen. So this is another way of writing. Right? Another way of writing is called as Fisher's projection. So how do you write Fisher projection? Fisher projection is a special type of projection or type of depiction where it is applicable for carbon with 4 valency where attached to different molecules. Let me give you an example and then we'll go for it. The example what I am going to take is tartaric acid. So in this case you have 4 carbons as usual. Okay, I am just going to draw the wedge projection of it. This molecule will be, this part of the molecule will be COOH. One of it will be hydrogen. While the other one will be OH. So if you take this molecule and if you try to write the Fisher projection of this, you can write it in 3 different forms. So you can draw like this. The upper line shows that it is above the plane. while the lower line shows behind the plane, while the other two lines are up on the plane. So now what are we supposed to do? First we will put the carboxylic acid on the top. Now the projection can be written like this, or you can write the mirror image of it. So these are the various forms of writing the tartaric acid. Either the OH and H can be on the same side, or the OH can be in the opposite direction. And all of them have a name, okay? This is called as meso-tartaric acid. This is plus tartaric acid. This is minus tartaric acid. Finish, ma?
Yes, sir.
Now we will take the same tartaric acid and we will write it in a different form. Okay. So I will take this as the first carbon and this as the second carbon. Okay, I'm going to take the tartaric acid and then I'm going to write the form. This is called as Newman's projection. So in case of Newman projection, we will take this first. So I will just number them. If I number, it will make a lot of sense. So 1, this is 1 and this is 2. So the front carbon I will draw like this. Because the back carbon you cannot see, because the front carbon actually stops the U of it. So COOH, OH. So again, if you write the second carbon will be like this. So the second one also you can write. So you can see the COH is in the top while the COH is in the bottom, right? So you can write the other one like this. So opposite of H you have another H. Opposite of OH you have another OH. So this is another form. The above one can also be written like that. For example, so the opposite of COH you have COH. So the opposite of H you have another H. Opposite of OH you have another OH. In this case, the opposite of H you have OH. So the second molecule is also similar to that. only difference is the position. So the OH is here, here H is here. So opposite of OH you have H. Opposite of this H you have OH. This is called Newman's projection or Newman projection. Copy this now. So these are the various methods by which you write or you project the molecule. So Newman projection, Fisher projection, wedge projection, bond line, condensed and expanded form. So this Newman projection, you can also draw one more form called sawhorse projection. So either you can convert to sawhorse to Newman or Newman to sawhorse, both are fine. So for example, if you take the front carbon as COOH, H and OH, so the back carbon is like that, COOH, H and OH. Likewise, you can draw for the other two molecules also. So this is called a sawhorse. Right? Can I move forward?
Yes, sir.
So the next important topic would be isomerism. Please make a note. So what do you mean by isomerism? Same molecular formula but different other forms. What are the other forms? It can divide into further two. The other form can be different structural formula, or it can be different stereoisomerism. So structural isomerism, so what is structural isomerism? It is also called as constitutional isomerism. Same molecular formula, different structural formula. Same molecular formula, different spatial formula. Spatial means in the space it will have a different type of formula, which is further constitutional isomer is further divided into five types. Number one, chain isomerism. Position or positional isomerism. Functional isomerism. Metamerism. Tautomerism. ring chain isomerism. So stereoisomerism is further divided into two types. One is called as configurational isomerism. Another one is called as conformational isomerism. So configuration is further divided into optical isomerism, and then geometrical isomerism. So I'll elaborate everything in detail. First you write down, just copy this. We will explain each and every isomerism in detail.
Copy, sir.
So shall we see one by one? Write down, the first heading would be chain isomerism. Or it is also called as nuclear isomerism, or it is called as skeletal isomerism. So what will happen in this case? Write down. So this isomer will have same molecular formula but different nature of carbon skeleton. What do you mean by different nature of carbon skeleton? Let me explain. So this is N-pentane. So what is the formula? CH3, CH2, 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 CH2. So now you take the same carbon, attach one of the carbon here. What is the formula? CH3, CH2, CH, CH3, CH3. So this is called as N-pentane or just pentane. So every time you can see one of the carbon is moving from the long chain to the branching. So if such a thing happens, it's called as chain isomer, nuclear isomer or skeletal isomer. So how do you name the second molecule? 1, 2, 3, 4. So 2-methyl butane. So the common name would be N-pentane is a common name. Similarly, isopentane. So this is called as 1, 2, 3. 2, 2. Dimethyl propane. We call it as neopentane. Copied ma? Same molecular formula but different nature of carbon skeleton. Finished, Amma?
Yes, sir.
Oh. So the next one would be position isomerism. So what is a positional isomerism? So position isomerism means it is applicable only for molecules with double bond or functional group. So it is applicable for what, ma? Molecules with double bond or triple bond, or it is applicable for molecules with functional group. So when I say positional isomerism, what is the definition? How do you write the definition? Same molecular formula but different position of functional group or double bond or triple bond. So for example, this is pent 1E, this is pent 2E. So if you write the name 1, 2, 3, 4, 5, this is pent 1E. 1, 2, 3, 4, 5. Pent 2E. Or you can have something like this. Same pentane. So this is 1-chloro-pentane. This is 2-chloro-pentane. This is 3-chloro-pentane. The position of the chlorine changes. Another mistake in your textbook, please make a note. They have given examples of ketones in position isomerism. Position isomerism, ketone doesn't come there. Position isomerism is only for the functional groups like chloro-bromo, not for C double bond O group within the chain. Okay, if the change is coming within the chain, we call it as metamerism. Can you see the textbook? First they have given molecular formula of C5H10. Next they are giving molecular formula of C4H9Cl. Third they are giving ketone. That is wrong. Please strike it out now. That is a wrong concept. So please do not misunderstand that ketone position, the change in the position of the ketone is also called as position isomerism. It's wrong. It is called as metamerism. In your text itself, they have given the ketones in the metamers, and again they have given in the position. So it is wrong. It is only called as metamer. Okay? Please make that change. Have you checked it and changed, ma?
Yes, sir.
So now we'll go for the third isomerism, that is called as functional isomerism. So there are many functional isomers, but in your textbook they have given only 2. So first we'll write the definition and then we'll move forward. So the definition for functional isomerism, write down. Same molecular formula but different functional group. Same molecular formula but different functional group. So they have given few examples like aldehydes and ketones. For example, you take 3 carbons. So you put double bond O here or double bond O here and balance the remaining with hydrogen. So you'll get CH3, CH2H, CH3, CH3. So this is called as propanal. This is called as propanone. So similarly you can compare the carboxylic acid and esters. So in this case again you take 3 carbons. So C double bond OH. I'll put the C double bond O here and put the other O here. And then the other carbon like that. So I'm removing the hydrogen and I'm putting it in somewhere else. So now you balance it with hydrogen. CH3, CH2, COH, CH3, CH2. So how do you name this molecule? This is called as propanoic acid. This is called as methyl acetate or methyl ethanoate. Finished, Amma? So same molecular formula but different functional group.
Sir, can I use the restroom?
Yeah. No problem. Go. Is the board visible?
Yes, sir.
So the next isomer is going to be tautomerism. So what is tautomerism? Tautomerism is a combination of position and chain isomers. So it is a special type of functional isomer. It's a combination of all the three. So two different structure is given for one single tautomer. So a single compound, because of the change in the position of the atom or change in the position of the double bond, it can become two different molecules. So there are two types in this. One is the dyad system, where only two atoms are involved. Another one is the triad system, where three atoms are involved. So let me give you an example. For example, you take hydrogen cyanide. So now what can be done? You can shift the hydrogen to the other side. So you'll get C triple bond NH. So this is called as cyanide. This is called as isocyanide system. So now we can also see another system called keto-enol tautomerism. So this is called as acetone. So what will happen to acetone in this case? Very simple. The hydrogen bond shifts here and oxygen will take the hydrogen. So what will happen? You'll get CH2 double bond C, single bond CH3 OH. So this is also acetone, no doubt, but the form changes. This form of acetone is called as the keto form. This form of acetone is called as the enol form. Another triad system is also there, that is called as nitro acinitro tautomerism. So this is again combination of bond and atomic shift. So HON double bond O. HON double bond O. So now what will happen? The hydrogen will shift to the nitrogen. So thereby you get O single bond and double bond O, where the hydrogen will be attached to the nitrogen this time. So this form is called as the nitrite form, and this form is called as the nitro form. So these are all called as tautomers, and these isomerism is called as tautomerism. Same molecular formula but different atomic systems, which happens due to the shift of sigma bond and atoms. Finished, Amma?
1 minute, sir.
Yeah.
Copies.
Okay, now let's go for the next isomerism. Write down ring chain isomerism. So same molecular formula but different ring or chain formula. Same molecular formula but different ring or chain formula. So for example, this is butene. So this is butane. If you check the formula, both will have C4H8. This is a different molecule. This is but1e. This is cyclobutane. You take the same formula, C4H8. Cyclobutane, methyl cyclopropane. So these two are examples of ring chain isomerism. Finished, Amma?
Yes, sir.
So in your textbook, I don't know, many mistakes are there, ma. So first we'll see one by one. So let's go for geometrical isomerism. Many mistakes are there, especially when they try to show the geometrical isomers such as cis and transformation. I think they have made many mistakes, like, they have simply left one carbon in the page number 136. Can you please go to page number 136? Can you see the
Yes,
box on the top?
Yes, sir.
How many carbons are there in the first molecule?
7.
Huh? Carbon ma
7.
11 ah? Ma there are
7. 7.
எப்படிமா 7 என்னம்மா படிக்கிற ஒழுங்கா பாருமா CH2 டபுள் பாண்ட் CH சிங்கிள் பாண்ட் CH3 3 கார்பன் தானமா இருக்கு இந்த பாக்ஸ்க்குள்ள பாருமா ஃபர்ஸ்ட் மாலிக்யூல் CH2 CH CH3 கரெக்ட்டா
Which page, sir?
136 மா ஜியோமெட்ரிக்கல் ஐசோமர்ல ஒரு பாக்ஸ் போட்டிருக்கான் பாருமா
It is in 135.
தெரியலையாமா
Found out.
யூ ஃபவுண்ட் அவுட்டா How many carbons are there in the first molecule? CH2, double bond CH, single bond CH3. Irka?
Yes, sir.
You check the other 4 molecules they have drawn. 4 carbon will be there. So these are all
Yes,
mistakes
sir.
in your textbook. So we will not follow that, okay? So what is geometrical formula? So geometrical isomers, write down. Same molecular formula but different spatial projection of carbon in an alkene. Very important. This is something you see only in alkene or cyclic compounds, or in case of alkadienes, or in case of alkadienes. So for example, you take CH3, single bond CH, double bond CH, single bond CH. What is the name of this molecule? Butene. Puridama? So how to draw the geometrical isomer? Are you following, Rifa?
Yes, sir.
So I'll write these 2 carbons first. C double bond C, C double bond C. And then you draw the bonds like this. So what all attached to the C double bond C? 2 hydrogen, 2 methyl. So the methyl can be on the same side, or the methyl can be in the opposite direction. While hydrogen can be in the same side, hydrogen can be in the opposite direction. So what do you call this? Both of them are butene, of course. This is called as cis-butene. Cis means same side. This is trans-butene. So very simple. Remember, among the two, which is stable? This is more stable. So what will happen? You just heat this molecule. So if you heat this molecule, the carbon, single bond carbon will be here. So the pi cloud will break. So methyl is here. Here the methyl will be here. Hydrogen will be here. Because it's the cis isomer. So what will happen in the next set? So as you continue, the bond will rotate in this direction. So when the bond rotates in this direction, what will happen? C single bond C. This pi cloud will be there as such. So if you shade it like this, after rotation, the blue goes on the top, the green goes on the bottom. So CH3 will be here. While here what will happen? The CH3 goes down. The hydrogen will be here, the hydrogen will be going up. Again what will happen? It becomes stable. So this happens on heating. So there is a rotation along CC bond. So this is what they tried to explain in your textbook, and they have done some nonsense. So cis-butene is unstable. So by heating the cis-butene, the double bond opens up and there will be a rotation along CC bond and becomes stable butene. This is what they have tried to do, and they have messed it up in the book. So try to write properly. So why trans is always stable when compared to cis? Because the bulky groups are in the opposite direction. The molecule will have less energy. Lesser the energy, greater the stability. So energy for this is less. It has more energy. So lesser energy means more stability. More energy, lesser stability. Done, ma?
Yes, sir.
So when you look into their chemical properties, both of them will have similar chemical properties. So chemically both are similar, but if you check their physical aspects, they will change. For example, you cannot separate them by any chemical reaction. Only physical methods like gas chromatography or fractional distillation, or by separating funnel different densities, you can do that. But it is very difficult to do with separating funnel, so we have to go for fractional distillation and gas chromatography. Okay. Shall we move forward? So one more example that is given in your book is buta 1,3 diene. In your textbook they would again 1,3 butadiene. Both are fine. You can write it in both the ways. So 4 carbon. So the double bond is the first and the third carbon. So the remaining you balance it with hydrogen. So it can be either the cis butadiene or it can be trans butadiene. I'm writing the bond line form. Trans buta 1,3 diene. Cis buta 1,3 diene. There is another example given in your textbook, but it is not called by the name cis and trans, but it is called as anti and syn. Let us see how that can be explained. Can I move forward?
Yes, sir.
So we are going to take the molecule called oxines. What is it called? Oxines. You can also use azo compound, but I don't know why they have not given. So I am taking only oxines. So oxines are nothing but R, N, double bond O. I'm sorry. R, C, double bond N, OH. These are called as oxines. So for example, you take CH3. C double bond N, C double bond. So the R can be CH3H. It is OH and the lone pair in this direction, or the lone pair can be in this direction, OH can be in the opposite direction. So if methyl and OH are on the same side, or hydrogen and OH are on the same side, we call it as the syn isomer. If the H and OH are in the opposite direction, we call it as anti-isomer. Syn is the cis equivalent. Please make a note. Anti is the trans equivalent. So this is what they are given for oxine.
Yes, sir.
Right, now we will go for optical isomerism. Again, remember, the optical isomerism given in your textbook is not enough. Okay, it is very less or inadequate. So you write it clearly and carefully so that you don't misunderstand anything. Okay, what is optical isomerism? Before going to optical isomerism, you should know about something called plane polarized light. So you take a light source So if you look at the light particle coming out of it, it will be vibrating in all the directions. So they have not given a clear picture, okay? If the picture is not clear, how will you learn the concept? So the light will be vibrating in all directions. What do you call this light? It is called as unpolarized light. This unpolarized light is passed through a material called polarizer, and the light which comes out of it will be vibrating in one direction. So unpolarized light will vibrate in all direction, while the light which vibrates in one direction is called as plain polarized light. So you take this plain polarized light and you can pass it through various solutions. So let me say this as sample A, this is sample B, and this is sample C. So inside that box some chemical materials are there, and we are trying to pass the same plain polarized light in all of them. Okay, are you clear, ma?
Yes, sir.
Please understand the concept, otherwise you will not be able to make it further, huh? So let me pass the light through sample A. So what is happening to the light? Nothing is happening to the light. The light is the same. When I pass it through sample B, the light is tilted towards right hand side, or the light will get tilted towards left hand side. There are only two options. So here the theta is positive. Here the rotation is negative. When it is left, negative, positive. Here theta is equal to 0. So you can say that because of the action of light, you can say that sample A, B, C. So what is the optical activity? So if a material doesn't rotate the light in any direction, we call it as optically inactive. B is called as, it is rotating the light towards right hand side, so it's called as D isomer or plus isomer. It is also called as dextro isomer. This is L or minus isomer. It is called as levo isomer. So if a light, plain polarized light gets rotated towards right hand side by a sample, such a sample is called as dextro or D isomer or plus isomer. If the plain polarized light rotates towards left hand side, where the theta value is negative, we call it as the levo isomer or minus isomer. Finally, if the sample doesn't rotate any direction, the plain polarized light gets unperturbed or it doesn't get disturbed by anything, the sample is going to be the same. After passing the light through the sample, the light is not getting deflected in any direction. We call it as optically inactive. While dextro and levo, we call the sample to be optically active. Please make a note. So optically active compound rotates the plain polarized light towards left or right, while optically inactive compound will not rotate the light in any direction. Is that clear? And remember,
Yes,
you should always use small d, small l. You should not use capital D, capital L. So this is what called as optical isomerism. So this is condition. But what all molecules will obey optical isomerism, we have to check. So for a molecule to possess optical isomerism, the only condition is it should have an asymmetric carbon, and one more condition is chirality. Can I move forward?
Yes, sir.
Have you drawn everything clearly, because it's not there in the textbook?
Yes, sir.
So now we are getting into the conditions for optical activity. Right now, so number one condition, asymmetric carbon. Number two, chirality. So what is an asymmetric carbon? So let me take an example called lactic acid. So what is the formula of lactic acid? CH3 C COOH OH H. Can you see the central carbon is attached to 4 different groups? Such a carbon is called as asymmetric carbon, and it is denoted by the letter star. So this is lactic acid. So you take the same molecule. So you have hydrogen here. So the mirror image will also have hydrogen here. So the CH3 will be here. The mirror image will have CH3 here. The COOH behind. In this case, COH behind, it will be in the front. And then you have the OH here, and the OH will be here. So you can see that they don't look like mirror image for you, but actually it is a perfect mirror image, because the CH3 in the front has gone back in the mirror image. The COH in the front has become which was behind has become front in the next molecule. So this is called as optical activity, and these two are called as D isomer or plus isomer. This is called as L isomer or minus isomer, and this is called as enantiomers together. So what is an enantiomer? So what do you mean by enantiomers? Isomers with non-super imposable mirror images. So what is an enantiomer? Isomers with non-superimposable mirror image. So what is an asymmetric carbon? A carbon attached to 4 different groups. And what is chirality? Chirality is nothing but it is the condition of forming a non-superimposable mirror image. So an enantiomer is a perfect chiral molecule because of its non-superimposable mirroring. That's all you need to know about optical isomerism from your textbook.
Orbit, sir.
Done, Amma? Now next topic, write down deduction of elements in organic compounds. This is our next topic. So what all elements will be there? So we will have carbon, we will have hydrogen, we will have nitrogen, we have sulfur, we may have halogens such as fluorine, chlorine, bromine, iodine. Okay, we may also have something called phosphorus. So we will see how to deduct each of them. So the first one is deduction of carbon and hydrogen. So can you see a molecule here? Can you see the picture here?
Yes, sir.
Just a moment, I will try to copy the picture and paste it. Okay, I think now it will work. Can you see the picture, ma?
Yes, sir.
So in this picture you can see that this is a picture used for the deduction of carbon and hydrogen. Draw this diagram first. So the organic compound is mixed with copper oxide and then it is heated. So when it is heated, what will happen? The carbon in the organic compound becomes carbon dioxide. The hydrogen in the organic compound becomes water. So the carbon dioxide will be absorbed by lime water, turns lime water milky, while the water will change the white color copper sulfate to blue color. So let me write the equation. on the top. So carbon reacts with copper oxide 2 times to give carbon dioxide plus 2 times of copper. The next one, 2 hydrogen reacts with copper oxide to give H2O plus copper. So now what will happen? The 5 water molecules that comes out of the copper sulfate, which is actually colorless, becomes copper sulfate pentahydrate, which is blue in color. So take the carbon dioxide and treat it with calcium hydroxide, which is nothing but your lime water. It becomes calcium carbonate. Plus water. This is a white precipitate. Please copy, ma. So the second experiment is lime water turning milky. So this is how the presence of carbon and hydrogen is detected. Have you drawn the diagram and the equations?
No, sir.
Copy, no problem. So similarly, we have deduction of nitrogen, we have deduction of sulfur,
Copied, sir.
copied. So now we will go for the next method. So using this method you can deduct nitrogen. Write down. Deduction of nitrogen in organic compound. So what is the first step? And there is a name for this method. I don't think it has been given in your book. Yes, they have not given. It is called as Lassane's test. I'll share the video in the link. You can go through the video and then you can understand this better after that. Okay, if I teach you now itself, it will be very difficult. I will share the video. Please go through the video and come back. See all the videos and before we go for the next class, because how they prepare Lassane's extract and how do they test for the nitrogen, how do they test for the sulfur, how do they test for various other things, I will send it first and then we will learn the equation. If you learn the equation beforehand and then you go for the video, you will not understand anything. So I will try to explain that there. So in today's session we started with various types of projections, and then we went into